Hey guys, today's lesson is on section 4.7 vertex form, and we're going to be writing quadratic functions in a different form. Remember, our standard form of a quadratic function is f of x equals ax squared plus bx plus c, or y equals ax squared plus bx plus c. The form for vertex form is under the title y equals a times x minus h squared plus k, and what vertex form tells us is the vertex of our parabola when we're graphing it on a coordinate plane. A quadratic equation in vertex form is a lot more convenient than a quadratic equation in standard form because it's a lot more easier to graph. The a, h, and k in our vertex form tells us the translations of how the parabola will move around the coordinate plane. The a value out front of the parentheses tells us whether the parabola will face up or down. If a is positive, it will face up, and if a is negative, it will face down. We knew that from the previous lesson when we were graphing using a table of values. In addition to telling us whether the parabola faces up or down, the a value, if it's greater than 1, tells us if the parabola will be stretched over the coordinate plane or a skinnier parabola than when a is 1, or if a is in between 0 or 1 or a fraction, it is going to be compressed across the coordinate plane. It is going to be a wider parabola than the parent function or than when a is 1. The h inside the parabola, if it's positive, tells us that it's going to move left, and if it's negative, it's going to move right. You might remember that from the section we did when graphing absolute value functions, that inside the parentheses or inside the absolute value signs told you left or right. It's the same thing here. And the outside value k, if it's positive, that will move the vertex or the parabola up that many units. And if it's negative, it will move down that many units. So on the right-hand side, I just have a quick example there for you, identifying a, h, and k. In the example in the square, the a value is 2. Since it's positive, it is going to be facing up or concave up. And since it's more than 1, it's going to be a stretched parabola across the coordinate plane, skinnier than when a is 1 or the parent function. The h value is -3. That means the vertex or the whole parabola will move right 3 units on the coordinate plane. And the k value is 1. Therefore, it's going to move up 1 unit on the coordinate plane. Just looking at vertex form, we could identify what the vertex is using h and k. The vertex is the opposite sign of h and k. So in this case, the vertex of this parabola would be 3, 1. In the problems below, we're going to do the same deal as the example at the top right. We're going to identify a, h, and k and describe the translation and the vertex of the parabola. Problem number 1 here, the a value out front is 3. Since it's positive, it's going to tell us that the parabola will be concave up. And since it's more than 1, it's going to be stretched across the coordinate plane. It is going to be a skinnier parabola than when a is 1. The h value is -1. When it's negative, that's going to tell us it's going to move right that many units, which would be right 1 unit. And the k value here is +2. If k is positive, that tells us the vertex is going to move up that many units, so it would move up 2 units. Looking at the h and k value, our vertex is going to be 1, 2 on the coordinate plane. Going over to the right, number 2, a is -2. Since it's negative, that's going to tell us that the shape is going to be concave down. The parabola is going to face down like an N. And since it is greater than 1, meaning just the value of 2, it is going to be stretched or a skinnier version of when A is 1. H in this case is going to be positive 1, and when it's positive, it's going to move the left that many units, so it will move left 1 unit. And K is negative 3. When K is negative, it's going to move down that many units, so the parabola will move down 3 units. Looking at the H and K values, we can write our vertex, which would be negative 1, negative 3. In addition, if our parabola vertex starts at 0, 0, and it moved right or left 1 unit and down 3 units, the vertex would end up being at negative 1, negative 3. And lastly, number 3, the A value, since there is no coefficient out in the front of the parentheses, will be 1. Our parabola will be concave up. However, it won't be stretched or compressed. It's going to be the same size as the parent function when A is 1. H in this case is negative 1. And when H is negative, it's going to move to the right that many units, which is 1 unit. And K is 2, which means the parabola will move up that many units, in this case 2 units. If we start with the vertex at 0, 0, and it moves right 1 unit and up 2 units, our vertex is going to be 1, positive 2. We can also tell that the vertex is 1, 2 in the original equation using the opposite sign of H and the value K. What I'm going to ask you guys to do is pause the video and try 4, 5, and 6. Once you get your answers, play the video to check. Here are your answers for 4, 5, and 6, identifying the translations in vertex. And number 4, since there's a negative on the outside of the parentheses, our A value is negative 1, telling us it will be concave down. And since the value is 1, it's not going to be stretched or compressed, skinnier or wider than the parent function. H value is 1, so it's going to move left 1 unit, and K is negative 3, so it will move down 3 units. Our vertex there would be negative 1, negative 3. To the right, number 5, the A value is 2. Since it's positive, it's going to face up, and since it's greater than 1, it's going to be stretched or skinnier than the parent function. H is negative 2, therefore it's going to move right 2 units. And there is no K value at the ends, therefore K is 0, and the parabola will not move up or down. Our vertex in this case would be 2, 0. Lastly, for number 6, our A value is negative 1/2. Since it's negative, it's going to be telling us our parabola will be concave down. And since it's a fraction, it's going to be compressed across the coordinate plane or wider than the parent function. As you could see, there's no operation inside the parentheses there telling us H is 0, so this parabola isn't going to move left or right. However, there is a K value at the end after the x squared, which is negative 2, so this parabola will be moving down 2 units, making the vertex 0, negative 2. Our next page here, we're going to practice writing a quadratic equation in vertex form. As you can see, the 2 problems at the top are in standard form of a quadratic equation. We have our model here of what vertex form is, and what we need to basically figure out is what the vertex of the equation is in order to write it in vertex form. How am I going to find the vertex? It's the same steps as when we graphed last lesson using a table of values. We'll first find the axis of symmetry using the formula x equals negative b over 2a. In this case, negative b is going to give us negative 6 divided by 2 times a is 2 times 1. Negative 6 divided by 2 is going to give us negative 3. So we know that the axis of symmetry in this case is x equals negative 3. And we could use that now to find the y value of the vertex. Remember, the vertex is on the axis of symmetry, the vertical line that cuts through the parabola, so they share an x value. Since our equation is y equals x squared plus 6x minus 5, I'm going to plug x equals negative 3 into our equation and solve for y. We're going to use the order of operations, so I'm going to do the exponents first. Negative 3 squared gives us positive 9. 6 times negative 3 is negative 18 minus 5. 9 minus 18 is negative 9. Minus 5 is going to give us a y value of negative 14. Now that I know the x and y value, I know that the vertex is going to be the ordered pair, negative 3, negative 14. Now that I know the vertex, we can now transfer these values into our vertex form, which is y equals a parentheses x minus h squared plus k. Y equals, what would the a value in this case be? Well, the a value in vertex form and standard form are the same. So in our standard form equation, the a value would be 1. So in the vertex form equation, the a value will stay 1. I'm not going to put the coefficient 1 outside the parentheses. We're just going to leave it blank. We'll now fill in h and k, in which we'll have x minus h is the x value of our vertex, so that's negative 3 squared, plus k is the y value of the vertex, in which we'll have minus 14. Make sure if you have a double sign inside the parentheses that we fix it so that it's x plus 3, because when you subtract a negative, we add minus 14. This is the vertex form of the equation in standard form for number 1. What I'm going to ask you guys to do is pause the video, try number 2 on your own. Once you get your answer, play the video to check. Here is your answer for number 2, putting a standard form quadratic equation into vertex form. We're finding the axis of symmetry first, in which we should use our formula x equals negative b over 2a to get positive 2. And using that x value to find the y value of our vertex, in which we get 5. Remember, when you're substituting 2 into your equation, you want to do the exponents first. 2 squared is 4, and then multiply negative 2 times 4. Since our vertex is 5, we can now just enter all the values or coefficients into our vertex form. A is going to be the same as in standard form and vertex form, which would be negative 2. The h is positive 2, so putting it into our vertex form model, we're going to have minus 2 squared, and the k is the y value of the vertex, being 5. The 2 problems below, we want to do something similar. We want to write an equation in vertex form. However, we're going to be given some different information. They actually tell us what the vertex is of the parabola or the quadratic equation, and instead of telling us what A is, they give us a point. So remember, our vertex form model is y equals A times x minus h squared plus k. What we don't know of this quadratic equation is what the a value is. We know what the vertex is, and they give us a point that this parabola passes through. This point can be substituted in for an x and y value. So notice our vertex is representing h and k. We have an x and y, so if we substitute these four values in, we would be left with a, and then we could write our vertex form model of our quadratic equation. The y value is -2. A is what we're looking for. It's the only thing missing in writing our vertex form. X is going to be -1 minus h is 3 squared plus k is 2. We're going to go ahead and simplify the right side using the order of operations, so we will do the parentheses first. -1 minus 3 is -4 squared plus 2. We'll then do the exponents to get a times 16 plus 2. We'll then go ahead and continue to solve the equation by subtracting 2 on both sides to get -4 equals a times 16, and divide 16 on both sides to finally solve for a. -4 over 16 can be reduced to -1/4. Now that I know the a value for our vertex form, including the vertex, we can now just substitute these values into the model here and write our quadratic equation in vertex form. We have y equals, a I just found out to be -1/4, times x minus h, which is the x value of the vertex, plus k, which is the y value of our vertex. Here is our vertex form, given the vertex of 3, 2, in which this parabola passes through -1, -2. What I'm going to ask you guys to do is pause the video, try number 2, and play the video back once you get your answer. Here's our answer for number 2 on the bottom of the second page. Since the vertex is -1, 0, that's going to represent our h and k values. And since they give us a point that this quadratic equation contains, or the parabola passes through, that would be our x and y. When we substitute this into our vertex form model, we're going to find that the a value is 2. Now that I find the only thing that it's missing, we could substitute the a and the vertex into our vertex form model here. Since k is 0, we're not going to do plus 0 at the end. We could just leave it as 2 times x plus 1 squared. The last page of our notes today, we're going to graph using vertex form and the 1, 3, 5 rule. As we saw in the previous lesson when we were using a table of values, there was a very specific pattern such that the 2 values next to the vertex were the same and the 2 values 2 units away from the vertex were the same. Even more than that, another pattern that exists is the 1, 3, 5 rule. From the vertex, the y values next to it, we're going to add a unit, then add 3 units, and then add 5 units. For example, problem number 1, this is already in vertex form for us, in which the vertex is going to be 1, 0. So let's go ahead and first plot our vertex at the ordered pair 1, 0 on our coordinate plane. Instead of making a table of values, we're going to use the 1, 3, 5 pattern to continue plotting the rest of our parabola. From our vertex, we're going to go over to the right 1 unit and up 1 unit. From the second point, we're going to go over to the right 1 unit, up 3 units. And if we had enough room, we would go over to the right 1 unit, and up 5. We're going to do the same exact pattern for the left side of the parabola. Left 1 unit, up 1, left 1 unit, up 3, and if we had enough room, we could go left 1 unit, up 5. We're going to go ahead and trace our points to graph our quadratic equation. Notice in this case the a value is 1, so we're going to have a positive parabola. It's going to be concave up, and we're going to use the 1-3-5 rule. We're only going to use the 1-3-5 pattern when a is 1. Remember, when a is a fraction, or when a is more than 1, it's going to make the parabola skinnier or wider. For example, I'm going to jump to number 3. The a value here is 2. So this is going to be a skinnier parabola than when a is 1, or compared to problem number 1. Instead of using the 1-3-5 rule, what we're going to do is multiply 1-3-5 by 2, and we're going to use the 2-6-10 rule. Once I plot my vertex, we're going to go over 1 unit to the right, up 2, over 1 unit to the right, up 6, and if we have enough space, we would go over, up 10. Our vertex here is -1, 3, so I'm going to go ahead and plot -1, 1, 2, 3. And again, now use our new pattern, multiplying it by 2, 2, 6, 10. I'm going to go to the right 1 unit, up 2, to the right 1 unit, up 6. And if I had enough room, I would go to the right 1 unit and up 10. I'm going to do the same for the left side, left 1 unit, up 2, left 1 unit, up 6, and we'll trace our parabola. Notice that this is much skinnier than the first problem we had. It is stretched across the coordinate plane. Notice 1, 2, and 3 all have a positive a value, so all of those would be facing up. 4, 5, and 6 have negative a values, so once we plot our vertex, we're going to go over 1 unit and use the appropriate rule to go down, so our parabola is concave down. I'm going to jump to number 5 here, and as you can see, the a value is -1/2. Since it's negative, it's going to be a concave down parabola, and since it's 1/2, it's going to be wider or compressed across the coordinate plane compared to number 1. I can't use the 1-3-5 rule here. That's only for when a is 1. I'm going to, just like when we did with number 3, multiply 1-3-5 by 1/2. 1 times 1/2 is 1/2. 3 times 1/2 is 3/2, and 5 times 1/2 is 5/2. So we're not going to move down 1, 3, and 5 units. We're going to move down 1/2 unit, then 1.5 units, and then 2.5 units. Let's first plot our vertex. In this case would be 3, 3. From there, we're going to move over to the right 1 unit and go down 1/2. Over to the right 1 unit from that point and go down 1.5. And if I had enough room to the right side, we would then go over 1 unit down 2.5. Let's go ahead and do it on the left side. From the vertex, left 1 unit down 1/2 box. Left 1 unit down 1.5 box. And left 1 unit again down 2.5 boxes. We'll then go ahead and trace our points to now graph our parabola. Notice that this one is much wider than what we had in the first example, and it's concave down because a is negative. What I'm going to ask you guys to do is try 2, 4, and 6 on your own. Number 2 will be concave up. We're going to use the same a rule as number 5, but go up that many units. Number 4 and 6 both have negative a values, so we're going to go down that many units. Be careful with number 6. Again, we can't use 1-3-5 what you're going to do is multiply 135 by 3 and use that new rule. Once you get your answers, play the video to check. Here are your answers for 2, 4, and 6. In number 2, our vertex is going to be 0, 0 because there are no operations inside the parentheses or outside. There is no h or k value, so we're going to start our first point at 0, 0. And we're not going to use the 1, 3, 5 rule. We're going to multiply that by 1/2. So it's 1/2, 3 halves, or 1.5, and 5 halves, or 2.5. So from our vertex, we'll go over to the right one, up 1/2, over to the right 1 unit, up 1.5, and then over to the right 1 unit, up 2.5. You would then copy that same pattern on the left side. Notice the a value was positive, so we have a concave up parabola. Number 4 has a negative parabola, and it's -1. So we could still use the 1, 3, 5 rule, but we're not going to go up 1, up 3, up 5. We're going to go down. Our vertex here is 3, 7. So we're going to start at 3, 7. And again, since it's negative, we're going to go over to the right 1 unit, down 1 unit, over to the right, down 3, and then over to the right, down 5 if we had enough room. Same with the left side, over to the left, down 1, over to the left, down 3, over to the left, down 5. Notice number 6 now has a 3 as an a value. It's negative, so it's going to be concave down. But since it's 3, I'm not going to use 1, 3, 5. I have to multiply that pattern by 3. So we're going to do the 3, 9, 15 rule. The vertex is -2, -1, so we'll go ahead and plot that first. The first value in our pattern is 3, so we're going to go over to the right 1 unit, down 3. We're going down because it's negative. Over to the right 1 unit, and then down 9. If we had enough room, we would then go over 1 unit, down 15. We're going to do the same pattern to the left. Left 1 unit from the vertex, down 3. Left 1 unit from from that second point, down 9. And that would be our final parabola. Notice how in number 4, since we had a value of -1, this is the same width as our parent function when a is 1 or -1. The negative just tells us it goes down. When a is a fraction, it is compressed, so it's wider. So number 5 is wider than number 4. And when a is greater than 1, as it is in 6, it's 3. Again, the negative only tells us that it's going to go down. It's going to be skinnier than when a is 1. As you can see, number 6 is skinnier than number 4. Please let me know if you guys have any questions, and I'll talk to you soon. End of video.